Lab 1 presentation. Lab 1 focuses on the physics of constant motion. The principles we must know include Newton's first law, which explains that an object in motion will stay in motion unless there is an external force acting upon it, and Newton's second law. The change in velocity of an object is proportional to the forces acting upon it. The purpose of this experiment is to compare a model version of this principle to a real-world observation. I decided to observe this ball rolling on a smooth wood floor. The ball weight is 40 grams and the ball diameter is 0.053 meters. I pushed the ball and allowed it to roll for a bit before recording. In Tracker, I used the ball diameter for the measurement of calibration. The origin of the axis was at the very first position of the ball, setting the initial position to 000 meters. Throughout this whole experiment, I neglected the y-axis due to the fact that we were experimenting with the x direction. The axis was positioned so that the ball traveled to the positive x direction. The time also started at 0 seconds and went to 0.767 seconds. Using the first 2 points, I calculated the initial velocity to be 1.20 and 0 meter per second by the velocity is equal to the change in position divided by the change in time. In order to create the model, I used the initial and final time, mass of the ball, and the initial velocity calculated, and entered this information into the GlowScript code. In order to translate Newton's law, we need to use the equation ball velocity equals ball velocity initial plus net force divided by ball mass or acceleration times change in time. We made the assumption that the net force was 0 and therefore the velocity will remain constant. We will explain why that is later. In lines 30 to 40, I set the initial conditions, and in line 48, we see that I start a while loop until the ending time, which is 0.767 seconds. And then in line 53, I set the net force to be 0, and in line 57, I entered the Newton's second law formula, and in line 39, I updated the position. With the information gathered by my observations and the model, I was able to create this position versus time graph. The blue line represents the model data gathered from the GlowScript code, and the orange dots represent my observational data. We expect our observational data to be exactly the same as the model data, as per our assumptions. So as we see the progression of the time, we can see that there's a deviation between our model data and our observational data. What does this mean? As we said earlier, Newton's second law translates to the equation shown. We can recall that Newton's first law says that an object will remain in motion until another force acts upon it. This can be demonstrated by setting the force equal to 0 in our equation. This sets the acceleration equal to 0, and therefore initial velocity will always equal final velocity. This gives us constant motion as shown by the linear graph for our model predictions. Because there is deviation from the model in our observation, this must mean that the object's movement was affected somehow. When the force is not 0, our final velocity will differ from initial, causing the nonlinear correlation. Therefore, we can conclude that our net force in our observation was not 0 the whole time. What if I had an axis orientation that made the ball go in the positive y instead of the positive x direction? This would not change the numbers in my results, but it would change the direction in my position and velocity vectors. Can we say how many pushes and pulls are added together to give a 0 net force? Something we need to understand about Newton's laws is that they only allow us to make predictions and models of motion. They do not tell us anything about the system or surroundings involved. In my observation, there were many forces that could affect the net force of the ball, such as friction and air. Based on the information we could gather, there is no way to be able to describe what force in our surroundings caused a net 0 force, or caused the little force that changed the velocity. In conclusion, Newton's laws have proven themselves to be quite accurate in predicting motion in a perfect system. In the real world, it is very hard to achieve a completely 0 net force, as we can see from my observations and the difference between the model and my observational data. However, we can utilize these laws to predict motion to the best of our ability. Thank you for watching!